First of all, thank you for the introduction and also for the invitation to give this talk. And please ask question, during the talk. And I try to make the talk as general. So I'll start maybe a bit slowly, and I'm guessing everybody will know the beginning, but slowly I'll ramp up. So the talk is really about anions in van der Waals materials. One second, I'll just put the cursor. So the talk is about anions in van der Waals materials. So let's start. So since the dawn of quantum mechanics, two types of particles have been identified: fermions and bosons. Their braiding statistics describe how the many-body wave function changes as two indistinguishable particles interchange position, causing an exchange phase of pi for fermions and 2 pi for bosons. Now, 40 years ago, there was a prediction that there could be more classes of particles carrying fractional charge and obeying fractional statistics. And because this question is important and fundamental, there were 4 decades of substantial theoretical and experimental effort trying to achieve this prediction. Now, let me just state, I would say there are a lot of works, but let me, state 2 of them. One is at 1997, which is the discovery of fractional charge by Glatley and Heibloom's group using shot noise measurement. And the other one is 4 years ago, the first indication of abelian braiding by Manfra and Feve's group in spatial and time domain braiding. Now, this experiment at 2020 was incredible in showing this abelian braiding, but more than that, it actually opens the window for experiment on non-abelian fractional statistics. In non-abelian fractional statistics, the many-body wave function doesn't only get to theta phase, but it completely changes. Now, this is important because, from one hand, it touches the foundations of quantum mechanics, where correlation and topology meets. And on the other hand, it's carrying the promise for platforms that facilitate quantum information processing, like topological quantum computation. So the potential gain here is immense. So now let's take a step back and have a bird's eye view on anionic fractional statistics. So the fundamental excitations are fermion and bosons, and maybe the simplest anionic excitation is the abelian anion. In the abelian anion, it obeys abelian statistics, where the many-body wave function get a phase, e to the I theta. And you can think of this new particle as kind of a spectrum of new particles between fermions and bosons. So now this phase can get any value between pi and 2 pi. Now, the more surprising are the non-abelian anions, where the many-body wave function completely changes. Now, non-abelian anions, they live on systems that have degenerate ground state. So basically, the ground state is spanned by some high-dimensional Bloch sphere. And you can imagine that your ground state, let's say, you begin in some vector in this high-dimensional Bloch sphere. And when you interchange to non-abelian anion, you basically do some rotation in this Bloch sphere. So you have some unitary metrics which basically describe this rotation. Now, these are the lowest order non-abelian anions, sometimes called Majorana zero mode. And you have also the more higher order non-abelian anions, which are called parafermion, which are similar in nature, okay? It has a different angle of rotation, and they also live on a high-dimensional Bloch sphere. Now, where can we find abelian and non-abelian anions? So it's actually, we have less systems that can create abelian anions, and it's kind of surprising that we have more ways to realize non-abelian. And one of the ways to realize non-abelian anion is by combining superconductor with topological insulator, superconductor with 1D semiconductor with large spin orbit, or ferromagnetic atomic chain. But my group is actually focused on the fractional quantum Hall effect. And there is a question here, fractional quantum Hall effect was actually discovered in 1982 when I was born. So 43 years ago. So, why actually to work on fractional quantum Hall effect? And the reason to that is because fractional quantum Hall effect has high mobility, high controllability, and long coherence. And this is actually three properties which are really necessary if you want to do this exchange and braiding experiment that I'll talk about. So what you see here is basically kind of an illustration of the even denominator fractional quantum Hall effect, which is basically a superfluid of pairs of composite fermion. And you can imagine that inside the superfluid you have vortices. And inside these vortices, you have the non-abelian anion. And what we want to do in the experiment is to braid these vortices. So that's basically, the aim of seeing braiding statistics of non-abelian anions. Now, what are the platforms? What are the experimental platforms that one can do this kind of experiment? So one platform is the gallium arsenide-based heterostructure. The other one is the graphene-based van der Waals heterostructure. Now, even denominator were actually also seen on zinc oxide and tungsten diselenide, but I would say that right now the systems that are more mature to tackle these questions of braiding are the gallium arsenide and the graphene-based. Okay, this system, we still need to develop more fabrication capability in order to tackle these questions in these platforms. Now, each of these platforms has its advantages and disadvantages. For example, gallium arsenide, because of the superlattice doping that one needs to create in order to see even denominator, has gate electrostatic instability. It also has relatively small energy gaps. On the other hand, graphene-based van der Waals heterostructure, the fabrication techniques are actually not well developed. We still need to develop some of them. You also do sequential fabrication, which means you do one device after the other. And for example, in gallium arsenide, you can do 32 devices in parallel. And that's actually, for an experimentalist, that's a very important advantage. So in my group, and what we'll talk about today is graphene-based van der Waals heterostructure. And if you want to look on even denominator in graphene-based, you can either go in the direction of monolayer graphene or the direction of bilayer graphene. Now, these are past results on even denominators in monolayer and in bilayer. And you can see that in monolayer, even denominator, it's even a bit hard to see, but basically this small line here and this small line are even denominators on monolayer. This is from Andrea Young's group. And you can see that you need 28 Tesla basically to see this even denominator. However, in bilayer graphene, these are works by Corey, but there is also another one by Andrea's group. You can see that on bilayer graphene, you can see a lot of even denominators, and they are even developed at magnetic field, which you can get in your lab. So around 18, 14 Tesla. So that's why, we kind of concentrated on bilayer graphene even denominator, and the experiment that I'll show you today are experiments that are going in the direction of looking at exchange phase or being more concrete on the braiding phase, which is basically twice the exchange phase, okay? Now, before I dive into the talk, if you want to look at exchange phase, you need interferometry technique. The two interferometry techniques that we have in the quantum Hall effect are the Febvre-Perot and Mach-Zehnder. And what I want to show you here is basically kind of a timeline that describes the evolution of this field. And we have two basically a platform that we are working with. One is the gallium arsenide, the other one is van der Waals. You can see that the gallium arsenide, right, is a bit older, but it has, strong muscles, okay? The graphene is a bit younger, but, it has larger motivation because it needs to get tenure. So, each of them has its own advantage. So in gallium arsenide, the odd denominator was seen in 82, even denominator at 87. In graphene, the odd denominator was seen in 2009, The even denominator was seen in suspended bilayer graphene in 2014 and in encapsulated at 2017. The first Mach-Zehnder in the integer quantum Hall effect was achieved in 2003 and the Fabry-Perot in 2009. In graphene, the Mach-Zehnder was done in integer quantum Hall effect was done in 2017 and in 2020. Penetrating into the fractional was first done by Manfred's group in 2019 in a Fabry-Perot seeing a Aharonov-Bohm oscillation, and then the same group saw abelian braiding. And this experiment basically kind of pushed us into this direction that I'm going to talk about. So following this experiment, there were a couple experiments in van der Waals in last year in 2024 showing abelian braiding, and I'll describe these experiments. But the main thing is, of course, going to the non-abelian braiding, okay, which that's kind of the most important goal. And what I'll talk about today is basically this part of the timeline, okay? So this is what I'm going to talk about, and more specifically, the experiment that I'll talk about will be braiding of non-abelian anions, okay, in bilayer Fabry-Perot, looking at the phase space of even denominators, okay, where we will classify the topological order of these even denominators, and then an interference study of even denominator. And basically these three steps in the future, I hope, will bring us to one of the core goals of the group, which is braiding non-abelian anions, okay? So my group has two core goals. One is braiding of non-abelian anion, and the other one is realizing parafermion. And basically everything that we do kind of emanates from these two core goals. So let me just, very quickly tell you what we do, and then I'll start the talk. One is looking at the excitation, looking at the braiding statistics. The other one is looking at the ground state and looking on its topological order. So here we are working on Fabry-Perot interferometry and Mach-Zehnder interferometry. And on topological order studies, we are looking on daughter states and thermal conductance. And in realizing parafermion, we are trying to create these hybrid structures of superconductivity and fractional quantum Hall effect, which is the third direction. So this is basically how we started 2.5 years ago with a tractor inside the lab. And this is how the lab looks like today. These are the fridges that we have. We are collaborating with the synthesis lab by Marcus Hooker, and we work in the submicron center. This is, by the way, something new in the last 3 years that we introduced in the submicron center. You can see here a glove box. This glove box has a transfer stage and an AFM, and it's connected into this ultra high vacuum tunnel, which connects to many, to ICP, to the position system, to ALD. And this system is more relevant into the last subgroup that I mentioned. Okay, so let's start. So I'll basically focus on bilayer graphene on even denominator state. The first part, I'll talk about topological order. We'll map the phase space of even denominators in bilayer graphene. And on the second part, we'll talk about the excitation and the braiding statistics. So first, very quickly, this is kind of the heterostructure that we work with. It's bilayer graphene encapsulated with HBN, encapsulated with graphites. It has few advantages, but if I want really to kind of pinpoint the important ones, so for Fabry-Perot, it's important that the graphite gate reduce the Coulomb energy. Okay, so that's so we use very thin HBN. Another thing, which is there is no doping layer. Everything is electrostatically controlled, and that's important because the gates are stable. And another thing that I'll show you that there is a wide variety of even denominator state. So how do we make the samples? We take these exfoliated flakes. We use the dry transfer technique, creating this heterostructure, and then we fabricate them. So let's look on bilayer graphene quantum Hall effect. So for example, gallium arsenide, every Landau level is twofold degenerate because of spin. For graphene, it's fourfold degenerate because of spin and valley. In bilayer graphene, it's eightfold degenerate because of spin, valley, and layer. Now, because bilayer, of course, is not two independent graphene, valley and layer are not good quantum number. So you basically have this new orbital. We call them the 0 orbital and the 1 orbital. And you can see the 0 orbital is basically only localized on one layer. The 1 orbital are localized on both layers. And that you'll see later, this is actually very important. And also what's interesting is that actually you can change the spectrum of the Landau level as a function of displacement field. And what do I mean? So what you see here, so the x-axis is the filling factor, or you can think about it like energy, and the y-axis is displacement field. And you can see that you have 8 Landau levels, right? 8 Landau levels because of spin, valley, and layer. And as a function of displacement field, you have many crosses between them. And this is actually, kind of a paradise for an experimentalist because you have many knobs that you can play here. Now, let's see which even denominator was seen in bilayer graphene, and what do I mean? So each of these is basically an integer Landau level. So you can look at it like this. And we are basically asking the question, where does the many body gap of the even denominator is open? So the first study, as I mentioned, was done in 2014 by Morfugo's group, and they saw -5/2 and -1/2. So you can see I kind of put dotted boxes on these places that they saw the even denominator. In 2017, Corey and Andrea saw the additional 3/2 and 7/2. So you can see these ones, additional places. And in 2022, Junzu's group saw the 5/2. They saw this even denominator. And this is basically, kind of all the even denominator that was seen up to 2022. So I can put it here, and one thing that immediately shouts on you is that you only see even denominator at orbital 1, okay? And only on orange, okay, right? Orange is orbital 1, blue is orbital 0. And that's actually something which is interesting, and I don't have time to talk about it, but a similar thing is happening in gallium arsenide. Now, what I'm showing you here is basically a schematic from Corey's paper, and this is Corey's paper, and I also added, Junzu 5/2 result and this line, and you can see that, so the x-axis here is filling factor and the y-axis is displacement field, and what I want you to see again is that, one second, that these even denominators are only seen on the pink one or the orange one that I showed you before, except for these 3 pockets of orbital 1. Okay, so for example, here, and here, even denominator were not seen. And this is basically where we enter to our study. So the first thing that we wanted to do is basically to do a phase space exploration. So we built a device and started looking at it. And what I want to show you now is what happened when we look on this pocket. So this is basically the result that we saw. So you can see on the upper and the lower one, this Shuvnikov-de-Haas oscillation that you see here. But previously, even denominator were not seen. Here you can see the even denominator forming. Okay, this is basically the half state. And now what we'll do, we'll make line cuts, in the 0 orbital and line cuts on the 1 orbital and look more closely. So this is the line cut at the 0 orbital. So you can see this Jane sequence, this Shuvnikov-de-Haas of composite fermion. And in the middle, you have a composite fermion liquid. You don't have the state forming. But when you change displacement field and you move to the 1 orbital, you see that you have this half denominator forming. okay? And this is exactly the composite fermion pairing. You also see, by the way, the Jane sequence, and you see something interesting. You see that the strength of the Jane sequence is actually reducing, okay? Because there is some competition with this composite fermion pairing. Now, another thing is you see these two small dips. And these small dips are actually a major, something which is very important here that will tell us a hint about the topological order of this composite fermion pairing. So just trying to summarize what I said up to now, this is the Jane sequence, for example, on the 1/3, and from the other hand, you have the composite fermion pairing at half. And we can think about it like a superfluid, which basically have, similar to a superconductor. And at some place, this condensation breaks, but similar to pseudo gap, okay, the pairs can still exist even after the condensate exited. And these states, which I described before, are called the daughter states. So what are daughter states? Daughter states are basically pairs of composite fermion, which have a charge now, unlike on the half where they are neutral. And they also feel some magnetic field, effective magnetic field. So these states are basically integer quantum Hall effect of pairs of composite fermion. This is kind of the intuition of what is a daughter state. Now, let's continue. If you go here to the left, you see a Jane sequence of Cooper pairs of four fluxes, of composite fermion of four fluxes. Also here on the first orbital, you can see this Jane sequence of composite fermion of four fluxes, also here. But as you go to the 0 orbital, you actually see a state here forming. And this state is the pair of four flux composite fermion. This is actually the 3/4 state which is forming. And also the Jane sequence is reduced. And the state that you see here, by the way, it's a small dip, but later when I'll show you 2D plots, you'll see that this is really a state forming. This is the daughter state of the composite fermion of Cooper pairs of four fluxes. So up to now, I described the half state. You can see here also the half state in the upper displacement field. You can zoom into the 3/2 state, and you can see the 3/2 is also forming. So basically, we see these three, pockets that previously people were not able to see this half filling state. Now we can also zoom into these white boxes. In the white boxes, we'll see the 3/4 state. So for example, this state is the -13/4 state. Here you can see the -5/4 state. And next to it, you can see the daughter state. Also here, next to it, you can see the daughter state. This is the 3/4 state with the daughter state and 11.4, okay? So if I try to summarize, because it's a lot of fractions, but if I try to summarize, so what did we add to the phase space? So basically, we were able to see the -3/2 and the half. So now we can add that we saw these three pockets of even denominator, which basically means now all the half filling state at orbital 1 were seen. Another thing, we saw quarter state or 3/4 states at all of these green regions, okay? And it's actually interesting that you see them only on each 2 Landau levels. So for example, here we didn't see them. And now basically the question is can we use this daughter state in order to learn about the topological order of these even denominators? So the question of what is the topological order is actually the question, what is the many-body ground state of the superfluid? So similar to BCS in superconductivity, we ask the question, what is the wave function of this ground state? And this we did together with David Bro's group and his student Misha. Now, what I'm showing you here is kind of, I don't know, an experimentalist diagram of, let's say, the device and measurement complexity of your device on the x-axis, and on the y-axis, your assurance of the topological order that you measured. And we can say that daughter state classification, and I'll explain what it means in a second, but daughter state classification are extremely easy to measure, but I'm not sure how true is this classification. Then, with complexity, you can do charge measurement, interface mode, and neutral modes. And the most definitive measurement, but also complex, is thermal conductance. But what's interesting is that it could be that actually daughter state, classification takes us all the way. But for that, we need to do thermal conductance measurement to this daughter state classification and kind of see that indeed our, let's say, prediction are correct. In a way, we need to know that, these daughters, really belong to this father. But, okay, so, what are daughter states? So daughter state, just to say it again, the 1/3 is integer quantum Hall effect of composite fermion. Daughter state are integer quantum Hall effect of composite fermion pair. Okay, I'm just, saying it again. And this direction started by Levin and Halperin in 2009. And last year, there were 2 theoretical papers by David and David's group and Nathaniel Linder and Adi and I forgot, but also Ashvin has a paper on this classification, where by seeing the daughter state, we are able to classify what is the topological order of the parent state. And let me explain what do I mean. Okay, so maybe 1 second before, so the first experiment seeing daughter state was in gallium arsenide at 2010, but they only saw one daughter state, so they couldn't fully classify the state. Then Junzu kind of reintroduced this idea of daughter states in bilayer graphene in 2020, and last year there were 3 additional papers on seeing exactly what Junzu saw at 2020. So what is daughter state classification? So what you can see here are basically all the daughter states possibilities, okay? And for example, if you see, let's say, this daughter state, and this daughter state, it means that the parent superfluid, ground state is the antifathian. And let me show you what I mean. So this is, for example, the half state measured at the orbital 1, and I labeled here all the possible daughter states, near these 2 dips, okay? And you can see that the purple lines are exactly hitting these daughter states. So that means that the daughter states is 6/13 and 9/17, which means the prediction is that this superfluid is the antifathian. Now, since we now see all the half-filling state, we can do the classification. We can do this classification for all the half-filling in the bilayer. And if you do that, what you see is that you either see antifathian or you see fathian. So basically, and this, you can look at this manuscript, but I'm not showing you here. But if you'll classify all the state here, it will either be antifathian or fathian. And let me color them. So for example, you see the green are fathian and the purple are antifathian, according to this classification. And you see that most of the even denominator are fathian, but when you have 2 1 orbitals which are crossing each other, the lower one is an antifathian and the upper one are fathian. So you can see here, this pocket, and this pocket, where you have this kind of crossing of 2 Landau levels of orbital 1, creating this antifathian. And we don't know, of course, if that's the reason that this is antifathian, but maybe it's a possible interpretation. Now, this is the state in half-filling. You can do a similar classification for 3/4. So for example, this is the 3/4, and this is the daughter state. Now, here it looks like it's a very faint, but you can see this is the 3/4, okay? And next to it, this line is basically the daughter state of it, okay? And the number of this daughter state is 19/25, but we don't see the other daughter states. So that means that if you see 19/25, it means that 3/4 is either anti-331 or an anti-Pfaffian, but we cannot conclude what it is because we don't see the other daughter state. So this schematic kind of showing you, all the observation that I mentioned, you can see that there is an interesting alternation between Pfaffian to anti-Pfaffian, Pfaffian, anti-Pfaffian, Pfaffian, anti-Pfaffian even in the half filling, and in the 3/4 we cannot conclude, but we kind of narrow down what is the topological order. So summarizing the first part of my talk, we see this alternation of topological order. We see a competition between Jane versus composite fermion pairing. And also something which is interesting, you see that the half filling are only created at the first orbital, but quarter states are only seen on the 0 orbital. And that's actually something which is also not understood. One thing that I'll just say, I'm not going to talk about it, but why do we see only 3/4 and not 1/4? And that's related to some follow-up work that we're doing now on Wigner crystal versus fractional quantum Hall effect, which is some other direction that we are working on. So now that we have this phase space, and here I'm going to change gears basically to the second part of the talk. So
Yuval,
now,
can I have a question?
yes, of course.
So among those you found the even denominator state, which one is the most stable?
Okay, so great. So -12 and 3/2 have they have the largest gap, okay? And in principle, I would say Pfaffians have a larger gap than anti-Pfaffian, okay? So Pfaffian state are roughly, 3-4 Kelvin, and anti-Pfaffian state are around 1 Kelvin. That's like the general, and you can see that we measured all of this. It's on the manuscript, but -12 and 3/2 are basically the strongest.
Yes, thank
Okay.
you.
Yeah.
I have another question. So you understand the edge structures of the daughter states?
I don't understand it.
Yeah.
I know it's a very complicated, actually, creature. So when I said it's an integer quantum Hall effect of pairs of composite fermion, that was kind of a heuristic. From what I understood, there are actually around 8 edge state there, something like that. But this, I think if you want to dive deeper, I think these theoretical papers by David and Nadia and Netanel explain these things very sharply.
Okay. Okay, yeah, thank you. Yeah.
Okay, sorry that I cannot give a more sharp answer here. So this is basically the kind of the even denominator phase space that we have. And now let's switch gears and talk about braiding phase experiment. So if we want to look at phase, basically we need to look at interferometers. And the two interferometers that we have in quantum Hall effect are basically the Fabry-Perot and the Mach-Zehnder. These are, the optical version. Here you can see the quantum Hall effect version of them. But what is the main difference between Fabry-Perot and Mach-Zehnder? The main difference is that Fabry-Perot is a multipath interferometer. Mach-Zehnder is a two-path interferometer. And that actually has an important implication because for charged particles, multipath interferometer gives you dwell time, gives you charging energy, and which is a disadvantage. We don't want charging energy, we want to see Aharonov-Bohm effect. On the other hand, for Mach-Zehnder, there is no charging energy. So that's an advantage for Mach-Zehnder. What is the advantage for Fabry-Perot? One is it's simpler to realize. You don't have this center ohmic contact. In Mach-Zehnder, you have this central ohmic contact, which makes it a bit more difficult. But even more important, Fabry-Perot, the manifestation of abelian and non-abelian braiding is actually very clear. It's phase jump and the odd-even effect. The braiding manifestation in Mach-Zehnder is just, it's more complicated to look at it, and this is why we focused on Fabry-Perot interferometers. So I want to go back, to 2020. This is a work that I did in Harvard during my postdoc together with Tom, looking at braiding of integer quantum Hall effect. So this is a graphene. So this is a van der Waals heterostructure that we fabricated in Harvard. And these trenches are basically trenches in the upper graphite gate. This is on graphene, and the cavity size is 3 micrometers square. And you define your QPC, okay? It's not etched all the way. It's only an etching of the upper graphite gate, okay? And now you tune your Fabry-Perot, okay? And you are able to have 2 QPC, and then you can create this cavity. So here we were able to see Aharonov-Bohm oscillation for integer quantum Hall effect. We saw it in parallel to Benjamin Sasepe's group in 2021 in graphene. 1 year later, Gleb Finkelstein group also saw it on graphene. And 2023, Junzu group also saw it on bilayer graphene. But all of these 4 works were basically discussing integer quantum Hall effect interference, and none of them saw fractional oscillation. And this is exactly, what I wanted kind of to do in my lab. So let's fast forward 3 years and also shift from monolayer to bilayer graphene. So this is a device we did in Weizmann. Basically, Jaehoon led this project, Jaehoon Kim, together with Himanshu Dev, and they created this Fabry-Perot. So this is now switching into bilayer graphene. The area is 1 micrometer square. Okay, we made it smaller, and there are also these bridges that let us control each QPC separately. And this is a zoom in to the device. Now, the first thing that you want to do, of course, is to see what you saw, 3 years ago, which is the integer quantum Hall effect. And this is indeed we see this Aharonov-Bohm effect for the integer case, which shows us 4 millitesla. And when you do the 2D FFT, you indeed see that you measure 1 micrometer square, which is exactly the fabricated area. But the most interesting is, of course, to go to the fractional quantum Hall effect. So now what do we expect? So since, it's a fractional charge, the Aharonov-Bohm, takes longer to acquire the phase. So you expect, instead of 4 millitesla, you expect 12 millitesla periodicity. Now this is the phase space of the 1/3 state. And what I want to show you here is something also which is nice. So of course, in blue, you see the 0RXX, which is measured on the right side of the device. And of course, if you want to stay in a constant filling of 1/3, you need to do some diagonal line, right? You need to, if you increase the density, you also need to change magnetic field in order to keep the filling factor exactly on the middle of the gap. So what we did here, we changed the center gate together with magnetic field, keeping all the time a constant filling factor of 1/3. And at each point, we change the plunger gate. And if you do that, you see this Aharonov-Bohm oscillation for constant filling. Okay, this is, this line here. And indeed, you measure 11.4, which is not exactly, 12 millitesla. Close, but this is it's an experiment. And if you do the 2D FFT, you indeed see that you get 0.35, which is 1/3 of the area, of the affected area, which is basically means, you see a charge of 1/3, okay? And this is just to remind that before we saw 1 micrometer square, And because we have a fractional charge, this is why we measure 0.35. So this is basically a measurement of the fractional charge. Now, what's interesting is that if you go along this line, you change the charge inside your Fabry-Perot continuously. But if you deviate from this line, okay, along this line, for example, you start occupying localized state. So now you have this knob of occupying localized states or not occupying localized state. So now if you measure again the same plot, but along this trajectory, you start seeing these phase jumps, okay? So this is the intermediate regime. And if you even go further into the third one, you see even more phase jump. And you can quantify this phase jump, and this phase jump, this is the statistical term that should give you 2 pi over 3. And if you do that, you see values which are, sometimes close to 2 pi over 3, sometimes not, okay? This is a measurement, along, the constant density. This is actually a measurement in constant magnetic field. And all of them show, close values to 2 pi over 3, but not exact. Now, let me show you kind of where different experiments are at. So this is the first experiment at 2020. You see also here, right? Values which are close to 2 pi over 3, not exactly. This is our study on bilayer graphene. There are 2 studies now on graphene by Philip Kim's group and Andrea Young's group, and also a work by Moti on optical Mach-Zehnder, which also saw phase jumps. So there are actually now 5 studies showing abelian braiding statistics on different platforms, okay? Different, gallium arsenide, graphene, bilayer graphene, Fabry-Perot, optical Mach-Zehnder. So it gives you the feeling that, we are there. We are seeing abelian braiding. Of course, we need to, do additional measurement. But what I want to show you now is basically that sometimes phase jumps are difficult to observe. For example, at Hall conjugate state. And then you need a different method to look at statistics. And that's what I want to show you now. I want to show you a new method of observing abelian exchange statistics. Instead of, and this is, doing jointly with Adi, Amit, which is Adi's students, and David. And instead of looking at one phase jump, we are actually going to use this knob of localized state. Jungkook, so I'm going to steal a bit of time from the Q&A part, okay?
Yeah.
Okay. And here we basically, follow this Arova, Schrieffer, and Wilczek paper from '84. So this is kind of a new formula that, Adi, Amit, and David introduced to us, which is actually encapsulate, and you can find it in this paper, which kind of encapsulate fractional statistics by looking at the flux periodicity. And I'm going to show you what I mean. So this measurement is basically the measurement that I showed you before in constant filling. But as you deviate from it, okay, you start introducing phase jump. But look at the line, these lines, the slope of these lines. They change their slope. You see they slowly, start to become parallel. Here they are almost completely parallel. Now they are even becoming negative. You can also go in the other direction, and you can see that they are becoming steeper. And this is all because of the state of this phase jump. And that was actually something interesting, that we observed. Now, what you can look at the flux periodicity as a function of this trajectory. And if you do that, you get this linear curve, this green line, okay? And you see that the flux periodicity is actually exactly this linear line, which follows this formula that I showed before. And the blue curve that you see is the standard deviation of the flux periodicity, if you look on the 2D FFT. So what you can do, okay, this is just showing, 4 points that you see basically taken from the previous slide. And, you can do a fitting here, and you can measure the fractional charge. okay, which is 0.33. And now you can look at this formula. And basically the unknown in this formula are the exchange phase and the capacitance between the localized state and the edge state. Now, if you assume an area of 1 micrometer square that we measure basically in the integer and also here on a constant filling, and you assume that your charge is 0.33. So because it's a linear line, you have two fitting parameters, the slope and the intersection, and you have two unknown. So you are able to extract theta 1, 2 and the capacitance. And if you extract this theta 1, 2, you expect to get 2 pi over 3, but you see a number which is close to it, 0.86. So 15%, away from the expected value. And this is basically another way to measure fractional statistics. And this is actually extremely important because you don't always see these phase jumps because they smear, but you can look at their averaged effect. And this is basically a new method of observing exchange statistics. I don't know if to say new, but it's basically kind of, instead of looking at the micro of every phase jump, you look at the macro effect of it. Okay, so this is the phase space that, I talked on the first part. And basically up to now, we looked on the 1/3 state in this point, okay? Now we can zoom out and look at other states. So for example, if we look on the minus...
Yuval,
Yeah.
sorry, can I have a
Yeah.
question? So
Yeah.
in the previous slide, you mentioned about the new strategy to
Okay.
getting the grading angle. Then the
Okay.
question is, here you have a capacitance. Can you determine the value precisely?
So what I'm saying is this capacitant is unknown, right? So we find it by this fitting parameter. Now the question is whether it makes sense. And it does make sense. It's like if you try to calculate, you get a value which is very close to this number, okay? But I'm not assuming a capacitance, I calculate it from the fitting parameters.
I see.
Okay? So basically, this is the formula. I assume I know A and E star, and because it's basically a linear line, so I have, the slope and the intersection with the y-axis of this green line, and I have two unknown parameters, I calculate what is theta 1, 2, and the capacitance. So I don't assume the capacitance.
I see. So what if we assume the area A as another fitting parameter, then do you have a more
Okay,
precise value?
so that's actually a really great question. So why do I assume 1 micrometer? So first, from the integer case, and I'll show you a bit later that why it's actually justified. But also here, actually, when you look at a constant filling, okay, on a constant filling, this point, basically, what I showed you before, it shows you 3 phi naught, okay? This 3 phi naught means that the area is 1 micrometer square, but the fractional state is 1/3 of the electron charge. Now, you are right that, I have an assumption here. That's why I wrote, assume. But I think it's legitimate because, that's what I see in the constant filling. But I agree with you. That's actually one of the, shortages, disadvantages of using a Fabry-Perot.
Mm-hmm. Yes,
But
yes,
that's
because the area itself could depend on the environmental parameters, okay, voltage and the magnetic field.
That's true. But again, I'm stressing that, this formula is in the Aharonov-Bohm regime. And you see that the constant filling brings you very close value to 3 phi naught. If I was Coulomb dominated, I wouldn't get this number.
Mm-hmm.
Okay.
Okay, yeah. Thank you.
Yeah. Okay. So I'll just push forward, a bit to get to the even denominator. So this is the 1/3 that I showed you before. You can also look at the minus 1/3 state. This is, what you see, and you measure also 1/3 of the state, 1/3 of the electron charge. You can look on 4/3 at this point. you see 0.24, it's a bit far than 0.3. We can actually understand it by capacitance calculation, but this is what we measure. You can also look at the whole conjugate state at minus 2/3, okay? But then you actually measure 0.7, which is interesting. I'll talk about it. And you can also measure 5/3, and then you see 0.6. Now, if I try to summarize, so both in the hole doping and the electron doping, for minus 1/3 and 4/3, we see an interfering charge, which is the fundamental charge. But for 2/3 and 5/3, we actually see something which is more reasonable to doubling or bunching of this fundamental charge, which is actually quite interesting why we see that. But I just want to point out also this paper in the optical Mach-Zehnder, which sees exactly the same effect. So now these were all constant filling. You can also look outside of it using this new method that I introduced. And you can see that the phase that you measure for 4/3 is very close. It's actually 0.98, 2 pi over 3. And for 5/3, it's 0.91. Okay, so it's basically a measurement of the charge and a measurement of the statistics using this method. But now what about even denominator? So now we will look on minus 1, 1/2, and the 3/2 state, okay? This point and this point, okay? And why do we look on this point? So this is exactly, the question that I was asked before. We look at these even denominator because they are the strongest. So that's the easiest place to look at. And if I do a line cut here, for example, and look as a function of magnetic field, this is the Venn diagram. So you can see beautiful, minus 1/3, minus 1/2, and minus 2/3. You can also look here, and then you can see the 4/3, 3/2, and 5/2. And now what you need to do is basically to measure the constant filling at minus 1/2. And when you do that, you see this Aharonov-Bohm effect, and the flux periodicity is 2 phi naught. That's why you measure a number which is close to 0.5. If you do the same thing for 3/2, you see a number which is close to 0.42, okay? Now, these measurements are actually, one of the first measurements seeing even denominator Aharonov-Bohm interference. And I'm just stressing here where is the area changing, because this is, for holes and this is for electrons, so, it might be confusing, but both of them are Aharonov-Bohm. And what's important here is that actually the flux periodicity is twice the fundamental charge, because one would expect to see 4 phi naught, but we see 2 phi naught. And if you add, this flux periodicity to the graph that I showed before, you see this similar behavior, okay? And what you see here, that actually the flux periodicity follows the filling factor instead of the fundamental charge, which is actually something which is really not understood. You can also look again at the statistics of the half state, of the 3/2 state, for example, and you see that it behaves like an abelian, 0.93. Now, it's not that it acts like an abelian, it's because the interfering charge is E over 2. So let me summarize. What are the findings?
Yeah, can I ask just one question? So basically for the whole conjugate states, this Manfra group does not observe any interference. So, but you observe the interference,
Yeah.
right?
So actually at 2019, when they published it, they did publish an Aharonov-Bohm for 2/3, but it showed E. And we do not observe E, we see
Yeah.
2E over 3.
Yes. But here, so basically, but this is you will have the neutral mode, so the upstream mode, right? So
yeah.
but still
But
you observe the interference. So
yeah.
do you have the explanation to have the interference, even though you have the neutral mode? So can you?
If I see something, I
Yeah.
see it, right? Why does it happen there? I don't know,
Yeah.
right? But
But
basically,
the interference is still
one-
clear then. Yeah. So this interference for the whole conjugate state is also even clearer than the interference in the particle states.
I think it's very similar. It's as
They're very
difficult.
similar. Okay.
It's
Yeah.
you can see here, okay?
Yeah.
It's the visibility of the whole conjugate state is as robust as the particle, and I'll tell you actually as robust as the even denominator.
Okay. Very good.
Can I
Yeah.
comment
Okay,
here?
maybe just because I have 2 more minutes, I'll just
Yuval, can I comment here to just quickly about why the neutral mode may not be, are you able to hear me?
yes.
Yeah, Jingho, that it is known that for the graphene, at least the thermal conductors length scale diverges. They don't talk to each other. The relaxation
Yeah.
length,
Oh.
they don't equilibrate this counter propagating mode in thermal energy. On the other hand, chemically they talk to each other. So it is now established. So that might be the reason there is no energy transfer between this counter propagating mode, and that could be the reason that even this whole conjugate, you can see this.
Okay. So it's a big, sharp difference
Yeah,
from the
from the gallium
gallium
arsenide.
arsenide. Yeah. Okay. Very
But
good. Yeah. Thank
but
you. Yeah.
actually, just to continue, what Anindya said is if you look on the optical Mach-Zehnder that Moti measured on gallium arsenide, so he also see interference there on whole conjugate state. But also there you have counter-propagating edges. So I'm just saying that you can ask the same question on Moti's optical Mach-Zehnder devices on whole conjugate state on gallium arsenide. So I'm not sure, even in gallium arsenide is, I support what Anindya said 100%. I'm just stating the fact that also optical Mach-Zehnder has counter-propagating neutral modes. Okay, but I'll just finish.
Wait a second. Anindya is here. So if Anindya is okay, can you spend a few minutes more?
Yeah.
I'm
Sure.
actually near the finish. So, okay, so let me summarize the finding. So I think it's one of the things which is really surprising is that the flux periodicity actually follows the filling factor and not the fundamental charge. That's something that we don't understand and should be addressed. And if you look specifically on even denominator, we observe doubling of the flux periodicity, which means that the interfering charge is E over 2, maybe, but still the localized charge are E over 4, okay? How do I know that? I know that by the statistical term, okay? Now, what are the open questions? So, of course, the open question is why the interfering charge follows the filling factor, and more importantly, how to break this doubling, okay? And that's, by the way, one thing which is very interesting is Moti's work on optical Mach-Zehnder. And the reason, of course, that we want to break this doubling is to go to the even odd effect and actually try to braid non-abelian anions. So, just to summarize what I showed you, so this is basically the first work which, we showed this phase space of quantum Hall effect in bilayer graphene. This is the integer quantum Hall effect, where we looked on integer states, okay? So, these white dots. This is from 2024. Here we looked on the interference on 1/3 on bilayer graphene. And this is the last work that we published a month ago, which basically looked at both particle and whole conjugate state, but also on even denominator states. And these are basically the experimental team, the theory team, and also there are other guys in the group which really contributed to this experiment, and we collaborate with the growth lab run by Marcus Hooker. So thank you. So this is basically the end of the talk.
Thank you very much.
Thanks.
Any questions? Feel free to ask question now.
So can I have one? Did you measure the tunneling charge by using shot noise? You may have some cross check.
Yeah. So we didn't measure. That's one of the things that we are trying, to do now. There is something which is, an experimental, let's say, challenge here, is that if you want to see even denominator, and you basically need to have top and bottom graphite gates. So I'm taking you a bit to, complication in experiment, but if you have top and bottom graphite gate, you need to use the silicon gate in order to dope the contact region, and that's actually creating noise in your contact. And then it's a bit problematic to measure charge, because that's what we started doing. But the charge that we see is the charge which is partitioning at the contact instead of the charge which is partitioning in the QPC. Okay, we have some idea now how to solve it, but indeed that's a very important measurement, what you said now.
Mm-hmm.
Basically, I'm just, I'm not telling it to you, to other people. That will distinguish whether the interfering charge is indeed E/2 or not. So that's a very important measurement, which should be done.
I
Can
have
I
one
ask?
question. Yeah. Did you observe the phase shift for the even denominator states?
Okay. So you do see phase shift, okay?
Yeah.
But the phase shift are not quantized, to, let's say, pi. But what I showed you, right, I showed it before, and this is, I think, also, kind of the strength of this technique of looking at the flux periodicity as a function of the periodicity. You see that, although you don't see clear phase jump, probably because of some smearing effect, you see their global effect, okay? And I didn't mention it, but for example here, what you see here are basically, the state of 4/3, 3/2, and 5/3. And of course, you can interfere the fractional inner modes, or you can interfere the outer integer mode. And you can see that there is no dependent on this trajectory for the integer, but you have a dependence for the fractional, which is exactly the statistical contribution, okay?
Okay.
So the short answer is no, we don't see, clear phase jump, but you see this statistical contribution in this formula.
Okay. Yeah. Thank you. Yeah.
Can I ask?
Yeah,
You
yeah, yeah.
have one thing I did not understand, Yuval, when you said that regarding your phase jump, when you are operating in constant feeling, you said there is no phase jump. You see pure unobserved oscillation kind of thing. Because because in a constant feeling, you don't change the number of quasi-particles or number of anions.
Exactly.
On the other hand, when you are scanning, constant, let's say gate voltage is fixed.
Yep.
Along a vertical line, for example, where your magnetic field is changing from your B star. So which means you have a number of anions you are changing. So I should expect the phase jump. But why the slope is also expected to change? I should see a phase jump, but eventually the slope will remain same, no? Or
so that's, I'll tell you something. And this is when we started this project, that's exactly the understanding that I also had in mind. But what we did is basically, really we just did this measurement and we saw that this line changes. Now, by the way, this is the constant density. This is the measurement usually people do, right? Constant density. They change only magnetic field. Now, you see this region is the 3 phi naught region, okay? This is actually the region, if I would zoom here, I would say I see 3 phi naught. But if you look globally, you see that the line is straight, okay? Now, basically what we did is, measuring this and then, kind of just analyzing it and seeing this straight line. Now, when you see a straight line, there has to be some explanation, some basic explanation. And then we came to Adi and David, and we understood that actually, this comes from, from this formula. And it actually comes from a Rovas kind of idea, but I think it's really a good point. Like we didn't expect this dependency.
So there's your first part of talk that four flux pairing,
Yeah,
and you mentioned about that you only could see for zeroth orbital, not the first orbital.
yeah,
But yeah, is there any, because you also mentioned zeroth orbital is a even parity, and for pairing you need a odd parity. So yeah, again, this discriminate, is there any theoretical understanding why do you see for zeroth orbital this four flux quanta pairing rather than the first orbital? I mean,
no,
naively, if I understand half filling for other thing, I would expect for the first orbital.
exactly. So the answer is no. There is no theoretical explanation why composite fermion of four fluxes happen at zero orbital. I didn't hear any, when I showed this, together with David and Adi, they didn't have some explanation. That's why, I kind of listed it here, because it's an open question. It's not clear why it is.
Yuval, I have one question. As I remember, the quasi-particle two-third, filling factor two-third, has temperature dependence.
Yeah.
So in your observation of the periodicity follows the filling factor has any relation with temperature?
Yeah, so that's really an excellent question, and I'm basically coming here to say no. So what we did, we measured, for example, the minus two-third, this measurement as a function of temperature, and we raise the temperature, and we look at this periodicity. And we expected basically that at higher temperature, it might drop to 0.3. Now, it didn't drop, okay? But I'll tell you something that, I think might be important is that if you look on short noise measurement, for example, you see that at elevated temperature, it comes from two-thirds to one-third. But usually these temperatures are around 100 millikelvin, 150 millikelvin. When you do the interference, I already lose the visibility around 100 millikelvin. So it could be that it's there, but it's at higher temperature, and I'm not able to see it. But that's really a good point. That's a fair point. And by the way, the same question you can ask on the even denominator. And we did the same thing on even denominator, and the flux periodicity didn't change. It stayed to phi naught.
So you're saying that it might have relation with temperature, but it's not observable in
I'm saying
interference.
no, no. I'm not saying not observable. I'm saying in my experiment I didn't see it. For example, maybe if you do the cavity smaller, then the energy spacing would be bigger, and
Yeah.
then you can go to higher temperature or something like that. But in our devices, we were not able to see it. I'll also say that I mentioned that Moti in the optical Machzender see similar effect, and also he tried to go into higher temperature and it didn't change. So it's not the temperature that
I see. Thank you again. Thank you very much.